For decades, the standard cosmological model provided the framework for how the universe grew. But in 2025, James Webb Space Telescope observations forced a reconsideration. By looking back over 13.5 billion years, Webb detected massive, highly developed structures that existing theories suggest should not have formed so quickly. This plots the predicted growth of early galaxies against the discovery of MOM-Z14. The model anticipates slow accumulation, but MOM-Z14 was brilliantly bright just 280 million years after the Big Bang. This massive gap suggests the early universe assembled objects at an unexplained rate. These discoveries suggest the early universe was a highly active environment, operating as a rapid factory for galaxy assembly. This rapid timeline is evident in a class of objects known as little red dots. One specific example, Canucks LRD Z8.6, appears in the data as it was just 570 million years after the Big Bang. Spectroscopy reveals that these red dots contain supermassive black holes consuming matter at rates that challenge current limits on early universe mass accumulation. When the universe was only 1.5 billion years old, galaxies were expected to be chaotic and unorganized. Instead, Webb identified Alaknanda, a massive galaxy with a highly structured grand design spiral similar to our own Milky Way. Finding such mature structures during this period suggests we are missing a fundamental mechanism in our understanding of how cosmic matter evolves. Moving from the edge of the universe into our own galactic neighborhood, the telescope operates as a spectroscopic laboratory. Webb uses its infrared instruments, NIRCam and MIRI, to analyze the molecular signatures of star formation. By reading these chemical signatures through thick clouds of dust, the telescope can track the specific elements being created or destroyed. This was demonstrated with supernova GRB 250314A. Webb worked with a global network of telescopes to analyze the chemical makeup of a stellar explosion that occurred when the universe was only 730 million years old. This same precision is now being applied to the Rocky Worlds program. Webb is probing the theoretical boundary where a planet's gravity is strong enough to retain an atmosphere against stellar winds, searching for signatures like methane or water on Earth-sized planets orbiting red dwarf stars. This shift has moved exoplanet science from simply identifying distant worlds to conducting detailed analyses of their chemical habitability. We can see the full range of this precision by focusing humanity's most powerful telescope on the small objects within our own solar system. In 2025, Webb tracked asteroid 2024 YR4, establishing it as the smallest target the observatory has ever studied. These observations provided critical data for planetary defense. By refining the asteroid's orbit, researchers confirmed that it would not impact the Moon. This chart compares the chemical ratios of local comets to those of the interstellar visitor 3I Atlas. Webb detected carbon and deuterium levels that are not found in our solar system, indicating the comet formed in a completely foreign environment. An instrument designed to see the first light in the universe is proving equally useful for defending and cataloging our immediate neighborhood. Webb even identified a 29th moon orbiting Uranus, a final testament to its resolution on local targets. All of these discoveries originate from this hardware, a primary mirror floating 1.5 million kilometers away from Earth. While the Hubble Space Telescope provided the foundational images of the previous generation, Webb has taken the next step by revealing the physical chemistry of the objects we see. The discoveries of 2025 have covered the entire cosmic scale, from revising early universe history to analyzing distant planet atmospheres and tracking local asteroids. Astronomy has moved into an era defined by high-definition chemical precision. Because of Webb's findings this year, the universe appears far more complex and more specifically knowable than we previously theorized. By uncovering phenomena that deviate so sharply from our predictions, the telescope is surfacing the specific evidence we need to identify the gaps in our current theories. One of the clearest examples is SNR 054069.3, the remnant of a star that ended its life in a massive explosion. The standard model for this type of stellar death involves a neutrino-driven mechanism. In this scenario, the star collapses and explodes with near-perfect symmetry, pushing a smooth, uniform shell of material into space. When Webb's instruments scanned the inner ejecta of this remnant, they found a point-symmetric morphology. Instead of a uniform shell, there are matching, irregular clumps and cavities mirrored across the core, suggesting the explosion was far more organized and directed than we assumed. This supports the jittering jet's explosion mechanism. It suggests that as a star collapses, it launches chaotic, opposing beams of energy that carve out the surroundings, rather than a single balanced blast. This evidence indicates that stellar death is a violent, jet-driven process. The physical shape of these remnants proves that the final moments of a massive star are defined by asymmetry and high-energy dynamics. Looking even further back, Webb has reached the era of cosmic dawn, when the first light began to fill the universe billions of years ago. According to our current understanding of gravity and gas accretion, a supermassive black hole should take billions of years to reach millions of solar masses. There is a physical limit to how fast they can grow. However, Webb has identified a population of compact, crimson objects known as little red dots. These are massive, growing black holes found in a period of the early universe where they theoretically shouldn't have had time to form. On this chart, we track black hole mass against time. These little red dots are outliers. They possess masses that are far too large for the age of the universe around them, challenging our assumptions about the speed of black hole growth. One hypothesis suggests these are black hole stars, super Eddington black holes so entirely blanketed in dense gas that they appear as single, massive red objects. The sheer mass of these objects suggests that galactic structures reached their peak size billions of years earlier than our current models of accretion allow. To find the bridge between these anomalies and the Big Bang, astronomers are searching for the universe's original foundations. This includes the hunt for population 3 stars, the first stars to ever form. They are expected to be pure hydrogen and helium, completely free of the heavier metals produced by later generations. Astronomers are also using the gravitational pull of entire galaxy clusters to act as a magnifying glass. This technique, called gravitational lensing, allows us to map the hidden pockets of dark matter that provided the original scaffolding for these early galaxies. Identifying these pristine stars and dark matter structures is the only way to build a model that explains how the universe went from a simple gas to the complex, massive structures we see today. Taken together, the 2026 Cycle 5 data suggests a universe that is far more active and evolves much more rapidly than we anticipated. The older, more static models are giving way to a view of the cosmos defined by high-energy jets, super Eddington accretion, and unexpected chemical enrichment. The consistency of these observations across different teams and instruments suggests these are not glitches in the hardware. We are seeing real physical events that require a more comprehensive theoretical framework. This is how scientific progress is measured. The most significant insights occur when empirical data forces a correction to our most established ideas. We are watching the data required to construct a new model of the early universe arrive in real time. These Cycle 5 discoveries provide the evidence that will define the next generation of astrophysics.